So now we want to understand that what happens if we are not strictly at t equal to 0 but very close to it, right? So we start off with the integral that we have defined. Now it's a fermionic system, therefore we put a minus that says that this is for a fermionic system where eta is equal to minus 1, and this we had defined as m minus 1 factorial 0 to infinity dx x to the power m minus 1 z inverse e to the power x plus 1. The idea is first to integrate by parts, and if I want to integrate by parts, so 1 over z inverse e to the power x plus 1, and integral of x to the power m minus 1 dx is going to be x to the power m 0 to infinity, and then I'm going to have 0 to infinity dx x to the power m over m, and I'm going to have d dx of 1 over z inverse e to the power x plus 1, right? So that this is going to vanish at x equal to 0, this vanishes, at x equal to infinity e to the power x diverges, so this is 0 in both the limits, and my m times m minus 1 factorial is 1 over m factorial integration dx x to the power m d dx of minus 1 over z inverse e to the power x plus 1. So I have f m minus of z is equal to this. Now I am very close to t equal to 0, so that we write the beta epsilon as beta mu plus t, and t is beta epsilon minus mu. Since I'm really very close to t equal to 0, you see the values of t will run from minus infinity to plus infinity, right? So that x is going to be ln z plus t, right? And dx is going to be dt, so that f inverse of z is going to be, this is the low temperature expansion we are looking at, very close to t equal to 0, minus infinity to plus infinity dt t plus ln z raised to the power m, substitute over here, and then you have d dt of minus 1 e to the power t plus 1, right? Z inverse e to the power x is going to be, z is e to the power beta mu, so that this is going to, x is going to be ln z plus t, so that you are going to have e to the power ln z plus t, which is going to be z inverse times z plus t, e to the, my mistake, z inverse times z times e to the power t, and this is 1, therefore you have e to the power t plus 1. Now this is a binomial expansion. I can do a binomial expansion over here, and this expansion is going to be mc alpha t to the power alpha ln z raised to the power m minus alpha d dt of minus 1 e to the power t plus 1. So that I can take ln z raised to the power m divided by m factorial outside, and minus infinity to plus infinity dt sum over alpha equal to 0 to infinity. I will have m factorial alpha factorial m minus alpha factorial ln z raised to the power minus alpha, and then I'm going to have d dt of minus 1 e to the power t plus 1. There is a t to the power alpha that is missing over here, so we include that. Now note that g of t, let's call this as t to the power alpha d dt of minus 1 e to the power t plus 1. If you note this, then you will realize that this is going to be g of minus t is going to be minus 1 raised to the power alpha. So if you substitute t for minus t, then you are going to get g of minus t as g of t. So if you look at it, then you see that if alpha is even, then g of minus t is exactly g of t. That means g of t is an even function. If alpha is odd, g of minus t is minus g of t, so that g of t is odd function. Now this we are going to utilize. Let's see how we are going to utilize. I can take this integral over here, so that I have ln z raised to the power m factorial sum over alpha m factorial alpha factorial m minus alpha factorial, and then I have ln z raised to the power minus alpha. I have integral minus infinity to plus infinity dt t to the power alpha d dt of minus 1 e to the power t plus 1. Now this, I have just now said that this is going to be an even function if alpha is even, and is going to be an odd function if alpha is odd. So that this integral minus infinity to plus infinity dt is going to be t to the power alpha d dt of minus 1 e to the power t plus 1 is going to be 0 when alpha is odd. And this follows from that the fact that when alpha is odd, gt is an odd function, and is going to be integration, there is going to be 2 factor dt t to the power alpha d dt of minus 1 e to the power t plus 1 when alpha is even. Good. So therefore I have fm minus of z is going to be ln of z raised to the power m factorial. I then have the sum over alpha, but now alpha only even values are allowed, so that I have m factorial alpha factorial m minus alpha factorial. I have ln z raised to the power minus alpha, and then I have a 2 0 to infinity dt t to the power alpha d dt of minus 1 e to the power t plus 1, right? If you are clever enough, then you will see that I can integrate again by parts, and I will come up that this integral is going to be 0 to infinity dt t to the power alpha minus 1 e to the power t plus 1, and this is exactly f alpha minus, so that I have, so if you want to recall, Hajumpa. So now I can combine this integral with 1 by alpha factorial and t to the power alpha d dt of minus 1 e to the power t plus 1, so that this is 1 over alpha factorial 0 to infinity. I can integrate by parts again here, and it's going to be t to the power alpha minus 1 e to the power t plus 1, so that you immediately realize that this function, if you recall, I had this as m minus 1 factorial to give me 1 over alpha factorial 0 to infinity dt t to the power alpha d dt of minus 1 e to the power t plus 1. I can integrate by parts this one again. So what happens if I integrate by parts? I can take this as the first function, so that you have t to the power alpha, then integral of dt gives you minus e to the power t plus 1 0 to infinity, then you have minus dt, derivative of this is t to the power alpha minus 1, and then you have essentially minus 1 of e to the power t plus 1. This vanishes and you have alpha minus 1 factorial 0 to t infinity dt t to the power alpha minus 1 divided by e to the power t plus 1. Strikingly familiar, right? Because this is f of alpha minus 1. So that my low temperature expansion becomes ln z raised to the power m divided by m factorial. I have sum over alpha, which are take even values of alpha allowed, twice f alpha minus 1 times m factorial divided by m minus alpha factorial, and then I have ln z raised to the power minus alpha, right? So this is the limiting value, limit of z to infinity fm minus of z. If you take this, this is the approximation that you get. So I can now write it down, m factorial, using the values of f this functions. It's going to be pi square over 6 m into m minus 1 ln z minus 2 plus 7 pi 4 over 360 m into m minus 1 into m minus 2 into m minus 3 divided by ln z raised to the power 4 plus higher order terms. Good. What do I do with it? Well, our starting point again is to look at the number density. The number density, we know that for a quantum ideal gas is g over lambda t f3 half minus z for a fermionic system, right? And I'm looking at the limit of z to infinity. So that means n lambda t over g is going to be ln z. M is 3 half, so I'm going to have 3 half factorial 1 plus pi square over 6 m is 3 half, and therefore I have 3 half into half, and I have 1 over ln z whole square. We'll keep it as higher order terms. The lowest correction is when this is equal to this, so that I have n lambda t over g is going to be ln z raised to the power 3 half by 3 by 2 factorial, and 3 by 2 factorial, you should note, is 3 by 2 square root pi over 2. So once you put in over here, and if you compute ln z from this term, you will see that you are going to get ln z is equal to beta epsilon f, which is the Fermi energy at 0 temperature. Then if I have this, I can write down ln z, invert this over here, which is going to be beta epsilon f 1 plus pi square over 8. ln z is beta epsilon f to the leading order, so we will write this as kbt over epsilon f whole square plus higher order terms raised to the power minus 2 by 3, right? Why is that? Because you see, to the leading order, I have determined that ln z is going to be beta epsilon, so exactly at 0 temperature, right? Which I also get it by ignoring all the other terms in the series. Once I have that, then essentially I have beta epsilon f raised to the power 3/2. If I look at this expression, this whole equation, I take this whole equation divided by 1 plus pi square over 6 times 3 by 2 times half 1 over ln z whole square. But ln z is equal to beta epsilon f. I am very close to the 0 temperature, so here I am going to write down beta epsilon f 1 by beta epsilon f whole square, which is nothing but kbt over epsilon f whole square plus higher order terms, and this is ln z raised to the power 3/2, right? So this then leads me to this equation, and you see that ln z is going to be beta epsilon f 1 minus 2 by 3 times pi square over 8 kbt over epsilon f whole square plus higher order terms, which is going to be beta epsilon f 1 minus pi square over 12 kbt over epsilon f whole square plus higher order term, so that the chemical potential very close to 0, not exactly at 0, since this is going to be beta mu, is going to be epsilon f 1 minus pi square over 12 kbt over epsilon f whole square plus this. So that as you go away from 0 temperature, you see that the chemical potential decreases with as a quadratic in temperature. So we looked at the chemical potential as a function of temperature, and you realize from looking at this equation that for small temperatures, which are less than epsilon f over kb, the chemical potential is positive, so mu is greater than 0. This particular quantity, epsilon f over kb, is called the Fermi temperature, Tf, right? In contrast, for high temperatures, mu is less than 0. Mu becomes, the chemical potential is negative, and the 0 crossing happens at temperature which is of the order of epsilon over kb, that is equal to your Tf of the order. It does not exactly happen at Tf, but it happens of the order of Tf. Now our next interest lies in looking at the pressure. So I know that beta p eta is g over lambda t f 5 by 2 minus of z, and I am looking at the low temperature expansion, and therefore I am interested in the expansion that we did a little while ago, right? This is the one. So we will only keep up to ln z up to this order, and therefore f of 5 by 2 minus of z is ln z raised to the power 5 by 2 divided by 5 by 2 factorial times 1 plus pi square over 6 m minus 1 is 3 by 2, m is 5 by 2 here, and I have ln z raised to the power minus 2 plus higher order terms, so that this expression is g over lambda t 8 by 15 the 5 by 2 factorial square root pi, and then I have ln z raised to the power 5 by 2. I have 1 plus 5 pi square over 8 ln z raised to the power minus 2 plus higher order. All I have to do now is to substitute ln z from the here. So let's do that. So ln z raised to the power 5 by 2 is beta epsilon f raised to the power 5 by 2, and then I have this term which is raised to the power 5 by 2, that is 1 minus pi square over 12. I have kbt over epsilon f whole square, which we will write down as t over tf whole square plus higher order terms raised to the power 5 by 2. And in this term I am going to replace, since I am looking at the leading order correction, I am just going to replace this ln z as beta epsilon f, which is t over tf raised to the power square plus higher order terms. Sorry, okay, this discussion comes a little later. So here just I am going to replace this by beta epsilon f, so that beta times p eta, the pressure, becomes g over lambda t 8 over 15 square root pi ln z 5 by 2 raised to the power 5 by 2 is beta epsilon f raised to the power 5 by 2. Then I have 1 minus pi square over 12. Since this bracketed quantity is raised to the power 5 by 12, I will use a binomial expansion to write it down like this way, and then I have t over tf whole square plus higher order terms times 1 plus 5 by 8 pi square t over tf whole square plus higher order term. Now let's look at this expression. I have g over lambda t 8 over 15 square root pi beta epsilon f raised to the power 5 by 2, and I want to express this in terms of the number density n. So even if you have forgotten how epsilon f depends on n, there is always a way out. Remember, you can always start from this expression, which is your epsilon f, and your Fermi wave vector kf is defined as 6 pi square n over g raised to the power 1 by 3, so that I have h square over twice m 6 pi square over n over g raised to the power 1/3, raised to the power 2/3 is going to be your epsilon f. This part now I split. I write down g lambda t over 8 over 15 square root pi times beta epsilon f raised to the power 3/2 into beta epsilon f, and it's this part I am interested in simplifying. Then I have to look at epsilon f to the power 3/2, and epsilon f to the power 3/2 is h square over twice m raised to the power 3/2, and 6 pi square over n over g is going to be your epsilon f raised to the power 3/2. So let's substitute. I have g over lambda t 8 over 15 square root pi h bar square over twice m beta to the power 3/2, this raised to the power 3/2. Now you should know where I am going. Things should be clear to you now. And then I have 6 pi square n over g. This part is just this thing. I have a beta epsilon f that multiplies this. G gets cancelled out, right? And then I have 1 over lambda t. I have 6 over 15 I have beta h bar square over twice m raised to the power 3 by 2. Now I have an additional factor 8, which I'm going to write down as 4 to the power 3 by 2, and I have a pi square, pi to the power 3 by 2. There is a pi square in the numerator, there is a square root pi in the denominator, that gives you pi to the power 3 half, and then finally I have n. So 1 over lambda t, 6 over 15, beta h bar square 4 pi over twice m raised to the power 3 by 2 times n. And if you simplify this, just this part, this is beta h square over twice m pi raised to the power 3 half, and which you immediately identify as lambda t. So this whole expression then boils down to 1 over lambda t. This is going to be 2 by 5, and then you have a lambda t and then n, so which is equal to 2 by 5 n. Don't forget that you have an additional beta epsilon f lying outside, so you have this. So therefore your beta p eta is 2 by 5 n beta epsilon f. Now I have to take care of this. This is to the leading order, it is 1 plus 5 by 8 minus, I have 5 by 24 t over tf whole square plus higher order term. So 5 by 8, 1 minus 1/3, that is 5 into 2 by 8 into 3, one gets it 5 by 12. Sorry. So this is 2 by 5 n beta epsilon f, 1 plus 5 by 12. There's a pi square somewhere, is it? Yes, there's a pi square which we have missed. So we will t over tf whole square plus higher order term. P eta, the pressure of the Fermi gas, is n beta epsilon f, n is 2/5 n epsilon f, 1 plus 5 by 12 pi square t by tf whole square plus. Now this behavior is completely unlike an ideal classical gas, because in an ideal classical gas at 0 temperature it has a 0 pressure. But I note that at 0 temperature the pressure of a Fermi gas, the eta is minus here, so we will put a P minus. We'll put a P minus, which is going to be 2 by 5 n times epsilon f. So even at 0 temperature the Fermi gas do exert certain amount of pressure. The pressure is not 0. Now the energy is 3 by 2 P times V, right? Which means I have 3/5 n times the volume times epsilon f, 1 plus 5 by 12 pi square t over tf whole square plus higher order terms. Now the specific heat is del E del T at constant volume, which is your CV, that is going to be 3 by 5 n epsilon f times 5 by 12 into 2t over tf square plus higher order terms. So a little more simplification gives me n epsilon f is kb, so that this is going to be 3 by 2. So a little more simplification gives me this cancels to give you 6, this cancels to give you 2, and the 5 cancels out. You have half n kb, and the epsilon is kbtf, so I will write down this as kbtf times t over tf square plus higher order terms, so that you have n kb. There's a pi square which we have missed. There has to be a pi square here. There has to be a pi square, half n kb, pi square by 2 n kb, and then I have t over tf plus order t over tf whole cube. These are my higher order corrections. So clearly you see that very close to the zero temperature, the specific heat is linear in temperature, and this is true for any arbitrary dimension you consider. We consider a three-dimensional case, but in any arbitrary dimension you consider, this is going to be true. So one can plot the specific heat with respect to temperature, and you will get a result which will look like this. And this is your, so this is Cv over nkb, and this is the classical Dulong-Petit limit, and here this part is going to be proportional to T over Tf, a linear scaling. Now, as we said that this is going to be linear in any arbitrary dimension that you consider. It does not depend on the dimension, and we will see that this is in stark contrast to a Bose gas. But the reasoning is very, very simple. Recall that at t equal to 0, the Fermi-Dirac, the occupation number looks like a step function. So when you increase the temperature, what you at most do is you basically have something which is like this. So you are exciting these many number of particles and taking them to a higher excited states over here. So this fraction goes over here, from here to here, the higher excited state. Now that number of fraction is T over Tf times n. And each of these particle carry an energy which is kbt. So that the total this is n kbt over times T over Tf, which is n kb. So we will not write equal to, but we will just say the change in the energy that happens from going from the here to here, the exciting because of thermal fluctuations that you have, is T square over Tf, and therefore your specific heat, which is proportion, which is basically delta E delta T, and therefore the specific heat, which is a derivative of this, will go as n kb T over Tf, and this result is surprisingly independent of the dimension of the system.